Hello everyone, this is the second lecture of this week. In the first lecture, we tried to have a general definition of general expression of stiffness matrix. Today we use this definition and find out the stiffness matrix for today and in subsequent classes for different structural components. And through that exercise, we'll try to understand the philosophy of finite element method. Okay. Now, let us recall if the stiffness matrix was last class we have seen that stiffness matrix is K is equal to integration over the entire domain, and what is the domain and all we have not yet defined. That depends on what kind of elements, what kind of components of structural segments you have. So, this is B transpose, which is strain displacement relation, then constitutive relation, and then again strain displacement relation, that is integrated over the domain. So, that was our relation, right. Let us use this relation. Now, let us take one example. Okay. It is with the strength of material, using strength of material and also using the direct stiffness matrix method, you can solve this problem. Okay. It is the problem is we have a bar. Remember, it is not a beam, it is just a bar which is subjected to say axial force. One end is fixed and other end it is axial force is say P. So, what we are interested in? We are interested in what are the displacements at different points, what are the stresses at different points and strain at different points. Okay. Now, so as I said in the last class, we will not discuss the theory of finite element method and all. We have the knowledge of matrix method of analysis, we know what is the philosophy of matrix method of analysis, and we also have the knowledge of solid mechanics, and based on that we are trying to solve it, we are trying to devise a method which is more general. Okay. So, like matrix method of analysis, let us divide the entire bar into several parts. Okay. So, let us divide into say you can divide in many number of parts. Okay. Suppose divide in 4 parts. Okay. So, this is node number 1, this is node number 2, node number 3, 4 and then 5. The same exercise we did for matrix method of analysis. And similarly, we have element number 1, say this is element number 1, then element number 2, element number 3, member number 4, like this. So, if we take any arbitrary element, say element 3, it is connected between node number 3 and node number 4 with the same way we did in this method. Okay. Now, then what we did in matrix method, direct stiffness matrix, for a representative element, for a representative structural component, it could be truss, it could be beam or it could be frame or anything. For a representative structural component, we derive the stiffness matrix. Let us do that exercise right now. For representative element, take any element, for instance, take an element like this, okay, which is, okay, take slightly. Take a representative element like this, okay, like this. Suppose this is connected between node number 1 and node number 2, right. This is node number 1 and node number 2. Now, since it is 1D element, you have just 1 degrees of freedom, means it is bar problem. So, you have degrees of freedom along the longitudinal axis of the bar. So, this element at this point your displacement is say u2, that is our degrees of freedom, and at this point displacement is u1, right. Now, suppose this is x1, x1 is this is x1 is the coordinate of that point and x2 is the coordinate of that point, and suppose length of this member is LE, where LE is equal to x2 minus x1, okay. That is the length of this member. E stands for length of that particular element, okay. So, this is the thing we have. Now, one of the first step required is that explicitly we have not done in case of direct stiffness matrix. You see, what is U1? U1 is the displacement at node 1 and U2 is the displacement at node 2. Now, if I want to know what is the displacement at any intermediate point between node 1 and between node 1 and 2, suppose any arbitrary point, I want to displacement at this point, what will be the displacement? Because we do not know that displacement, we know the displacement only at node 1 and not at node 2. So, what we need is, we need to interpolate this based on the what is the displacement at node 1 and node 2, we need to interpolate this value, we need to interpolate at this particular point. Okay. Now, for that, assume that displacement between node 1 and node 2 varies linearly. Okay. So, suppose displacement which is a function of x that varies linearly a x plus b. Now, a and b are the constant which we do not know, we have to find out that constant, but then we need some information to find out that constant. And what information we have? The information we have that u at x is equal to x 1, that is equal to a x 1 plus b, that is equal to u 1, right. And then similarly, u x is equal to x 2, which is x 2 plus b, that is equal to u 2. So, we have two equations and two unknown, therefore, we can solve for a and b. And that was the reason why we assumed this variation is linear. We cannot take quadratic variation because we do not have sufficient information. Now, if we solve them, then what we have is, we have that a is equal to u 1 minus u 2 divided by x 1 minus x 2, that is the expression of a. Okay. That is important. Now, once we have this expression for a, we have to find out the expression of b. Now, how do we find out? We substitute any equation. If we substitute that, let us do that. So, a will be, if we take this expression, the first one is a is equal to u 1 minus u 2, u 1 minus u 2 by x 1 minus x 2 into x 1 plus b is equal to u 1. So, from this expression, if you solve that, we get b is equal to u 2 x 1 minus u 1 x 2 divided by x 1 minus x 2, x 1, this is b. Okay. So, this is important. Now, once we know a and b, then what happens? Then if you substitute this relation in this expression, then we get a functional representation of u. So, u x will be then a into a is this. So, if we substitute x 2 minus x 1 as LE, then it becomes u 1 x 2, no sorry not that, this one, this become u 2 minus u 1 divided by LE, and then into x plus b, b is this one, b becomes u 1 x 2 minus u 2 x 1 divided by LE, that is the expression for u. Now, if you write this expression, from that what we get is just little bit of manipulation of this. What we get is x 2 minus x divided by LE into u 1, this is very important, x minus x 1 by LE into u 2. This is very important expression. Now, let us write this expression as u x is equal to n 1 function of x u 1 plus n 2, which is also a function of x u 2, and where n 1 is equal to x 2 minus x 1 by LE and n 2 is equal to x minus x 1 by LE, right. This is important. These n 1 and n 2 are called shape function. Okay. Now, what is the advantage of writing this u in this expression? Because now, if we want to find out u at any intermediate point, you substitute corresponding coordinate in this expression and get the value at any intermediate point. If you substitute x is equal to x1 here, you will get u1. If you substitute x is equal to x2 here, you will get u2, and for any intermediate point you get a combination of u1 and u2. And what is the basis of arriving at this equation, this expression for n1 and n2? We assume that the variation, the variation of u vary along the length of this element linearly. We can have quadratic variation, we can have cubic variation for different kinds of element, okay, and we will get shape function accordingly for that. These shape functions are important. Before this shape function satisfies certain property, and before coming to the property, let us plot this shape function. Let us see, if I plot it along the length of the member, how this shape function look like. Okay. So, do this exercise. Suppose, okay, so x1 is, if we plot x1, so x2, if we n1 was how in, if we write once again, n1 was x2 minus x, not x, it is x2 minus x divided by LE, and n2 was x minus x1 by LE, right. Now, if I plot it, suppose this is the member, this is x1 and this is x2, and plot n1. If I plot n1, then the n1 will be at x is equal to x2, n1 will be 0, and x is equal to x1, n1 will be 1, like this, and between this will be like this. Similarly, if I plot n2, n2 plot will be this. So, this is for n2 and this is for n1. It means, okay. Now, it means that now this property, if you say, see n1, if I calculate n1, but x2 that is equal to 0, and n1 at x1 is equal to 1. Similarly, n2 at x2 is equal to 1, and n2 at x2, n2 at x1 is equal to 0. So, this means that n I at xj, that is equal to delta ij. Delta ij is called Kronecker delta. Delta ij means delta ij is equal to 1 if I is equal to j, otherwise 0. You look at this same. So, these shape functions satisfy Kronecker delta property, right. This is one property, important. Now, the next is, we just now have seen that u is equal to, at any intermediate point, u is equal to n1 u1 plus n2 u2, right. Now, consider a case, for instance, this is the bar element. Consider a case, at this point you have u1 and at this point you have u2. Now, suppose this is moving like this as a rigid body. If it moves like this, then what happens? Throughout this length, the displacement is this displacement is constant. So, u1 will be equal to u2 because it is moving entire thing as a whole as a rigid body. So, in that case, u1 will be u2, right. So, u1 will be u2. Now, if u1 is u2, u1 is equal to u2, what will be the intermediate value, intermediate u at any intermediate point? This will be same as u1 and u2. Okay. So, for rigid body, rigid body movement, rigid body displacement, what happens? Say u1 is equal to u2, suppose this is equal to u, okay. So, or some alpha, some constant, some alpha, okay. And then what happen? Alpha is equal to n1 alpha plus n2 alpha, and this gives you very important property, n1 plus n2 is equal to 1, okay. And if I more general way, if I write that n1 at any point plus n2 at any point, that is equal to 1, right. This is called partition of unity property, means if you take any point in the element and sum all these safe functions, this safe function, this summation will be equal to 1. If it is not 1, then this condition is not satisfied. The rigid body motion, your displacement and all the points are same, this condition is not satisfied, right. So, this is equal to, these are the some properties of safe functions. Okay. Now, once we have the safe functions, our objective here, if you recall, our objective is to find out the stiffness of this element, right. Now, let us do that. So, now next is once we have this, next is, if you recall, epsilon is equal to what? Epsilon is the definition of epsilon. Epsilon is equal to the first derivative of displacement. Okay. Now, here it is just one displacement you have and one strain you have. So, this is equal to strain, since it is one value. So, I am not writing in a vector form. Strain is equal to, if you du dx, right. This is the definition of strain. Since it is one component, we can write it, it is not partial derivative, it is just du dx. Now, that is equal to d dx of, now u we just now have, u is equal to n1 u1 plus n2 u2, right. So, can we write this as, this is equal to that dn1 dx dn2 dx, this, and then we have u1 u2 and then dot product in between. Okay. It is same as this. So, this is equal to what? This is strain. Now, you see, this is essentially what? This is essentially strain displacement relation. So, this is essentially epsilon is equal to b into u, epsilon is equal to b into u, where b is equal to, in this case, b is equal to strain displacement relation d1 dx and dn2 dx. Now, expression for n1 n2 already we have, this is n1 and this is n2. Okay. Now, if I differentiate it with respect to x, we get something. If I differentiate it with respect to x, what we get? If we differentiate it with respect to x, we will get d1 dn1 dx is equal to minus 1 by LE, and this will get plus 1 by LE, right. So, what we get is minus, this is equal to minus 1 by LE, if we take common, minus 1, this will get 1. So, this is equal to b, right. This is the expression for b we have, strain displacement relation. Great. So, once we have that, so what is the expression for expression for d? Expression for d is, we have the stress is equal to d into, that was our expression, that d into epsilon, right. Now, in this case, since it is just a 1D bar problem, it is your d is essentially Young's modulus E, right. So, here we have sigma is equal to d or E into epsilon, right. So, d is essentially E. So, we have found out what is expression for d, what is expression for b. Let us now find out what is the expression for the stiffness matrix, and that stiffness matrix expression, we use the general definition of stiffness matrix, and that definition, if you recall, that was this: the stiffness is equal to integration over the entire domain of this into B transpose D into B, and that integration is over the entire domain. Now, in this case, entire domain means, if you see this problem, in this case entire domain is the length of the member. Okay. So, it is essentially either you can integrate from x1 to x2, or we can integrate from 0 to LE. Okay. Now, if you do that, let us do this exercise. So, this expression will be, so k will be, let us write it here. So, k will be okay, use a different, okay. So, k will be integration over 0 to L E, length of this element, then B transpose will be this. So, transpose of this will be 1 by L E. So, it becomes minus 1 1, or you can okay. Now, then we have D, this D is essentially E. So, we can write it as E, and then again B is 1 by L E and minus 1 and then over D dx, okay, because it is integration over the length. So, we can take these outside, we can have E by okay. Now, one more thing, since it is integration, this integration has to be over the entire this integration has to be over the entire domain. So, entire domain will be what? Entire domain means in this case entire volume. Entire volume means cross sectional area multiplied by the length. Okay. So, cross section we have to multiply it by cross section as well, A into dx. So, now we can take this out, the entire thing out. If you do that, we are almost, by now you might have understood that what expression we are going to get, 1 A by L E square, and then this becomes 1 minus 1 minus 1 and then integration 0 to L E dx. Okay. This essentially gives you A E by L E 1 minus 1 minus 1 k. Now, please see whether you have seen this or not. What is this? We have done it for truss analysis. This is the stiffness for truss member in a local coordinate system. And truss member means what? Truss member is, we have force only in axial direction, right. The same element we are talking about here, we have a bar element which has force only in longitudinal direction, and this is the stiffness matrix. The same stiffness matrix we used in direct stiffness method, but that time we arrived at this stiffness matrix in a different form, right, in a different way. But now we have arrived this stiffness matrix in a more general way. The reason is, now you may ask that once we at the end, if you are going to get the same stiffness matrix, then what is the point of all this exercise? The reason is, this will allow us to derive stiffness matrices for different kinds of element. It is just not for truss. For demonstration, we are using truss, we will be using beam and other two-dimensional structure as well, but this will allow us to construct the stiffness matrix for a general class of segments, which was otherwise not possible the way we derived for in matrix method of structural analysis. Okay. Now, if you recall, this beam was divided into 4 parts. Now, similarly, we can, for every individual part, we can calculate the stiffness matrix for every individual part. So, for this part we can calculate what is K1, then K2, K1, K2, K1, then we can have K3, K4 and so on. So, 4 stiffness matrices, the same way we can have 4 stiffness matrices, but only difference for different stiffness matrices, your x1, your these coordinates will be different, and the eventually your length will be different. You get this stiffness matrix. Now, once we have this, so this stiffness matrix is essentially it corresponding to, so if you recall, this is for U1, this is U2, this is for U1, this is for U2. Okay. Similarly, we can have stiffness matrix for each bar segment, and once we have these bar segments, once we have the stiffness matrix for all the bar segments, we have to assemble them exactly the same way we assemble stiffness matrix in direct stiffness method, right. So, this was the assembling part. The next is the nodal load vector. Now, nodal load vector is, if you look at this structure, the nodal load vector will be, how many, what will be the size of the stiffness matrix? Size of the stiffness matrix will be, we have 4 nodes. So, total global stiffness matrix size will be 5 by 5. Similarly, nodal load vector, the size of the nodal load vector will be with the 5 elements, is a vector with 5 elements, and all elements will be 0. Only thing is for F5, for P5, this will be P, right. So, this essentially will be nodal load vector. Once we have the nodal load vector, then we can apply the boundary conditions exactly the same way we applied boundary condition in matrix method. And then once we apply the boundary condition, we can partition the matrices, stiffness matrix, and then calculate the unknown displacement exactly the same way we did it for direct stiffness method. Once we have the unknown displacement, the rest of the process is exactly same as the method. So, only difference between the methods that we have discussed in the last 7 weeks and the approach that we have just now discussed lies how we are calculating the stiffness matrix, the member stiffness matrix, and that is not a very small difference that we will subsequently see that is a very huge difference, okay, and that makes our life that allows us to calculate stiffness, this expression to construct stiffness for a very general class of elements. Okay. Now, this was for bar element. Similarly, we can have we can define the stiffness matrix for beam element, stiffness matrix for any other kinds of element. We'll see subsequently. But the beauty is, irrespective of the element, whether it is a bar element, beam element, or any other element, this expression will remain same. This expression will remain same. Depending on the elements, we have different degrees of freedom, and therefore, we have different strain displacement relations, and depending on the dimensions of the problem, we have expressions for D, but the general expression for stiffness matrix, this will remain same. Okay. Now, so next class what we do is, we do the similar exercise, but for a beam element, where the degrees of freedom will be the degrees of freedom will be translation, vertical, transverse displacement, and the rotation, and then see what is the corresponding stiffness matrix, and we will compare that stiffness matrix to the stiffness matrix we already know. So, with this I stop here today. See you in the next class. Thank you.